Good morning, students. Yesterday, we discussed what is the force acting on a charged particle when it is moving in a magnetic field. And we discussed an important case when a charged particle is moving perpendicular to the magnetic field, then how it moves and what is the force acting on, what is the work done, what is the time period of rotation, frequency and all. Okay. Today, when a charged particle is moving in the magnetic field at an angle theta, that theta is other than 0, 90 and 180. We know when the charged particle enters the field, moves in the field at an angle theta or 180 in the direction of the field, it experiences no force and it moves just undeviated. When it enters the field at an angle 90, yesterday we discussed in detail, it moves in circular path. When the charged particle moves making an angle theta with the field, we know it moves in helical path, right? Let us discuss. X, Y, Z axes, which are mutually perpendicular, coordinate system. A charged particle, see here, the magnetic field is acting in this direction. Along X direction, magnetic field is acting. A charged particle a positive charged particle entered the field, entered this field with velocity v, entered like this, making an angle theta with the field. Making an angle theta with the field. It just entered the field. See, for my convenience, it is entering the field, making an angle theta with the field. Okay. Then what happens? It moves in a helical path. Observe how it is moving. See, when it enters, it moves in a helical path. What that path is? See here, this is the path. It moves in this path. We know it experiences a force which is perpendicular to both V and P. It experiences force inward like this. Then it moves in helical path. Like this. This path as this magnetic field direction as an axis. Because magnetic field is spread in this as magnetic direction as an axis. See, if it is the magnetic field direction, If a charged particle enters like this, it turns surrounding of this, right? In this way, moves in that helical path. Okay. First thing, in this case, what is the force experienced by that charged particle? And what is the radius of this helical path? And how much distance it moves in one rotation? Those questions we get in exam. Okay, let us see. See this velocity of the particle, charged particle. It is making an angle theta with the field direction. It is not exactly along the direction of the field. It is not perpendicular to the field. Resolve it into two components. Its component along this field direction is V cos theta. V cos theta. Its component in the direction perpendicular to the field is V sin theta. This velocity components along the field direction is V cos theta. Perpendicular to the field direction is V sin theta. Okay. Whenever particle moves along the direction of the field, it experiences no force. That we know. Means this V cos theta component does not contribute in force. See this component, V sin theta component. Whenever a particle enters the field, it is just like a particle entering the field perpendicularly with this velocity. It moves in circular path, that we know. So due to this component, it moves in circular path. Due to this speed, it moves forward. V cos theta is the speed in the direction of the field. This makes it the particle to move forward. This component makes the particle to rotate. You understand? This is the component which is responsible for rotation. This is the component which is responsible for translation. The speed is acting in this direction, along the direction of the field. So due to this component, it translates, it moves forward. Due to this component, it rotates. As a result, it rotates as well as translates. That combinedly gives you a helical path to the particle. Okay. So which component is responsible? V sin theta component is responsible for rotation. Here, component perpendicular to the field. Perpendicular component. See, I took a symbol V perpendicular is V sin theta. V sin theta. Okay. Then, so whenever it is in rotation, it has some radius. See, there is some radius of the path. Let that radius of the path is some r, radius of the path. When it is rotating, we know force due to magnetic field supplies the necessary centripetal force. Yesterday we discussed. See here, Fc is equal to Fb. Fc is what? mv perpendicular square by r. Fb is what? q v perpendicular into b. Because here due to perpendicular component only it rotates. That is why I am taking simply perpendicular component. See, one v component goes on both sides. R is equal to mv perpendicular by qb. mv perpendicular by qb. See here, R is equal to v perpendicular is v sin theta by qb. This is R. Observe the difference. When it enters perpendicularly with the velocity v, yesterday we got here v. Here now perpendicular component is v sin theta. So here I got v sin theta, that's all. What is the time period of rotation here? What is the time period? To find the time period, of rotation. See here, can I write like this? M R omega square is equal to Q V perpendicular B. Here M R omega B perpendicular into omega Q V perpendicular into B. On both sides perpendicular component get cancelled out, velocity component. So omega is equal to QB by M. What is omega? 2 pi by T. So can I write 2 pi by T is equal to QB by M. Then time period T is equal to 2 pi M by QB. This is time period. You observe the time period of rotation, time taken to complete one rotation. The time period has 2 pi constant, mass of the particle constant, charge Q and magnetic field B. There is no velocity component in that. So yesterday we discussed time period and frequency and angular velocity are independent of the time period. Here also same. Okay. This is the time taken to complete one rotation. So here it is not only rotating and it is translating. It is translating. So how much it translates in one rotation? How much it translates along the direction of the field in one rotation is called pitch. Pitch of the particle. See, distance traveled in one rotation. Here I am writing. Distance moved or traveled by the particle, charged particle along the direction of field, along the direction of the field in one rotation. In one rotation, how much distance it travels? In one rotation means, for one rotation the time taken is t. So in that time period t, how much distance it travels? See here, let us start from any point. I start from here. Observe. See, it moves from, if it starts here up to here 1. When it starts here up to here 1. So distance moved in one rotation is this. In one rotation, it moves from here to here. This you call it as pitch P. Pitch, capital P, represented with. See, in horizontal direction, you have velocity, v cos theta. Time taken for one rotation, t, 2 pi m by qb. Distance traveled, velocity into time, because this velocity is not changing. with the same velocity it is moving, uniform. Velocity into time taken, that gives the distance traveled in one rotation. So from this, pitch P is equal to velocity component V cos theta into T, because T is the time for one rotation. What is T here? V cos theta 2 pi m by q. So totally, which is what? 2 pi m v cos theta by qv. That's it. This is pitch. Okay. So based on this question, on this concept, you may derive an expression for pitch. Okay. Come on, note down. The terms are as usual. B is magnetic field, V is the velocity, and theta is the angle between V and B. Q is the magnitude of charge. This path, trajectory of the path is helical, taking B as an axis. Around this B, it rotates like this. Well, let us go to next topic. Force acting on a current carrying conductor in the magnetic field. Force acting on a current carrying conductor in the magnetic field. Force acting on current carrying conductor or current carrying wire in magnetic field. One of the important concepts. See here, magnetic field is acting in this direction. So these lines represent magnetic lines of force. That means what? Magnetic field is acting in this direction. B. In this magnetic field, a conductor current carrying conductor is placed. A current carrying conductor of length L, area of cross section A, placed in the magnetic field in such a way its length making an angle theta with the field direction. It is kept in such a way its length is making an angle theta with field direction. Right? So what you have here? B. Magnetic field intensity or strength. L. Length of conducting wire. Length of the conducting wire. A. Area of cross section of wire. Area of cross section of wire. This conducting wire is placed in this magnetic field. Let theta angle made by L, length of the wire, with field B. With field B. Okay. Then what is the force acting on this whenever current flowing through this? Listen carefully. It is a current carrying conductor, means some current is flowing through this. Let current is flowing in this direction. Let I is the current. Through the wire. I current is flowing through the wire means what? Electrons are moving from one end of the wire to the another end of the wire. Already in electricity we discussed. Current is flowing in the wire in this direction means electrons are moving from one end of the wire to another end of the wire with an average drift velocity Vd continuously. Yes or no? Current flow is due to continuous flow of electrons inside the conductor in a particular direction. Means what? Electrons are moving in this direction with a velocity Vd. Each electron is moving from this end to this end in it with a velocity Vd. See, some number of electrons they flow from one end to the another end. Each and every electron is in motion with velocity Vd. Each and every electron is a charged particle now which is in magnetic field. So as it is a charged particle, it experiences a force. Each and every electron. There are some number of electrons are moving. All the electrons experience the force. If you add them, the total force acting on all the electrons, that is equal to the force acting on the conductor. This is the concept. Okay, let us see. So in this conductor, let electrons are moving with drift velocity Vd from one end to another end, right? In this conductor, number of electrons per unit volume, let us say small n, number of electrons per unit volume, small n, total volume of the conductor, volume of the conductor. Volume means area of cross section into length, AL. Now, what are the total number of electrons moving? Total number of electrons moving. Number of electrons per unit volume, small n. Total volume is AL. So total number of electrons moving, N. What can I write? A, L, N. Volume into number of electrons per unit volume. A, L, N. I got total number of electrons. What is the total charge? Well, total number of electrons moving. What is the magnitude of force on each electron? Magnitude of force on each electron, Fe. What is the formula? Electron is a charge. Force acting on a charge in the magnetic field, we know. Q VB sin theta. Here Q means charge of the electron. E VB sin theta. E VB sin theta. Force acting on, magnitude of force acting on each electron. Then what is the total force acting on the conductor? There are how many number of electrons? Total number of electrons, ALN. Force on each electron, EVB sin theta. Then what is the total force acting on the conductor? The total force acting on all the electrons which are moving from one end to another end. If you calculate, that is equal to the total force acting on the conductor. See, now total force acting on conductor. Total number of electrons into force on each electron. Okay. So what I get here? See. N. A. L. N. F. E. E. V. V. Sin theta. Okay. Here I said current flowing through the wire. Current flowing through the wire in terms of drift velocity, you have a formula. What it is? We know Vd is equal to, I am writing here, see, drift velocity. Drift velocity, Vd, I by Ane. You have this, sorry, I by A small n into E. Is it not the formula? From this, I is equal to Vd into Ane. I is equal to Vd into Ane. Second one. From 1 and 2, what we can write? From 1 and 2. Here, drift velocity Vd. Vd, Ane. Ane Vd. That is equal to I. Okay. So from 1 and 2, what we can write? Come on, note down. Next step I'll write. I'm rubbing this part. See here. From 1 and 2. From 1 and 2. See. Total force acting F is equal to A L, I keep aside, A N V D E, A N V D E B sin theta. Is it not the one there? A N V D E is I. So can I write L I B sin theta? This is the force acting on a conductor. Okay. And we can write it in vector form. F bar is equal to I L cross B. Here, length of the conductor is treated as a vector. I L cross B. right? This is its vector form. So LIB sin theta or BIL sin theta. You can easily remember BIL sin theta. One of the very important question. Come on, note down. Okay. When that force is maximum, when that force is minimum, let us see. See what formula I have? F is equal to LIB sin theta. If case 1 theta is 0 or theta is 180. What is the meaning? This is field. You place the conductor in the field like this. Current is flowing in this direction. This conductor is placed parallel to the field. Current is flowing in the direction of the field. In the direction of the field, theta is 0. Second case. This is B. You place the conductor in the field, C parallel. Current is flowing in this direction. Opposite direction of the field. Field is in this direction, current is flowing in this direction. Opposite direction of the field, theta is 180. In both the cases, see there, F, B, I, L, sin 0. B, I, L, sin 180. In both the cases, it is 0. Okay. Second, if theta is 90, means the conductor is placed perpendicular to the field. Conductor is placed perpendicular to the field. Then what happens? Current is flowing in this direction, either upward or downward, but perpendicular to the field. In this case, maximum force it experiences. Maximum. Okay. Come on, note down. If it is at certain angle, this is the formula. BIL sin theta. Okay. Next one. On this, we have some problem. A current of 3 amp. In your problems, problem number 11, I think. A current of 3 amp. 3 amp. Flowing in a linear conductor having length 40 centimeter. The conductor is placed in a magnetic field of strength 500 Gauss. And makes an angle 30 degrees with the direction of the field. It experiences a force how much? What is the force acting on it? That is the problem. Okay. Which formula? Whatever we used here. Force acting on the conductor. BIL sin theta. But if you observe the problem, here it is in centimeter. Here you have a unit Gauss. Gauss is the CGS unit of magnetic field, strength of the magnetic field. But if you convert it into SI unit, 1 Gauss 10 to the power of minus 4 Tesla. SI unit is Tesla for the magnetic field strength. So 1 Gauss is equal to 10 to the power of minus 4 Tesla. Convert it. Then substitute it here. B 10 to the power of minus 4. I you have L 40 into 10 to the power of minus 2. Sin 30. Sin 30. How much? Half. Then solve it. Okay. See in the exercise first problem. In the exercise first problem, a proton enters a magnetic field of flux density. Proton. What is the charge? E, 1E. 1.6 into 10 to the power of minus 19 coulomb. Enters a magnetic field of flux density 1.5 Tesla with a velocity 20 into 10 to the power of 7 meter per second at an angle theta is 30. The force on the proton is what? The force on the proton is what? What is the formula? QVB sin theta. Solve it. You have the data. See that second problem. Two particles A and B. Two particles A and B of masses MA and MB respectively and having the same charge. This is particle A, this is particle B. Its mass is MA, its mass is MB. Having same charge, Q same, moving in a plane. A uniform magnetic field exists perpendicular to the plane. Okay. The speeds of the particles are VA and VB. This is VA, this is VB. And the trajectories are as shown in figure. The trajectories of those two are shown like this. Dot means field is acting out. Trajectories of those two particles A and B, they are given like that. Options are given in this way. MA less than MB. Second option, MA greater than MB. MA less than MB and VA less than VB. MA is equal to MB and VA is equal to VB. Which option is correct? That is asked. What is the formula for the radius? Radius of the circular part? We know R is equal to MV by BQ. Given masses are different, velocities are different, this B same, this Q same. Given in the problem, which are having same charge and both are moving in the same electric field, magnetic field. Dot means field is acting outward, same magnetic field. If these two are same, R is proportional to M. See here, for second one, this is RB. For the first one, RA. Right? So, RA less than RB. That means MAVA is less than MBV. Right? That is the answer. which is A and which is B here. This is given as A and this is given as B. Sorry. So here RA is greater than RB. This is given as A and this is given as B. So which is the correct answer? This is correct answer. This is given as A and this is given as B in the problem. Okay, like that. Tomorrow we solve the remaining problems. Be in the class with your book volume. Okay, thank you.